Hello and welcome to everyone. Welcome to the fifth episode of the Math Plus seminars of Sabancı University SIAM chapter. Today we will talk about Math Plus cryptography, and we will focus on the homomorphic encryption. Our guest is Professor Erkay Savaş from Sabancı University. Let me introduce you briefly our guest. He received his bachelor and master degrees from Istanbul Technical University and pursued his PhD in Oregon State University. Currently, he is here in Sabancı University serving as professor and also dean of the FENS faculty. Now, hocam, it's your turn. Thank you for coming.
Hello, everyone. Thank you very much for the nice introduction. So happy to be here and basically, talking about, what we have been doing for the last 10 years. So I'm a cryptographer and I'm working in applied cryptography. So today I'm going to talk about a very brief, very simple introduction to lattice-based homomorphic encryption. And so I'm just going to, Okay, so this is the lecture plan. I'm going to basically provide you with the motivation for homomorphic encryption, what it is, and why we need it, right? In what kind of applications, we use homomorphic encryption, and maybe some other related, advanced cryptographic algorithms. And I will give you the definition of the fully homomorphic encryption later, and because there are partial homomorphic encryption and fully homomorphic encryption schemes. And I'm going to basically give some mathematical background. So I'm assuming that you are interested in the mathematical, aspects of this cryptographic algorithm. And I'm going to basically talk about a textbook homomorphic encryption scheme, meaning that this is not really the one that we are using in practice, which is very close to what we are doing, and basic concepts is there. So this is a kind of a simplified homomorphic encryption, so that helps us to understand the basic mechanism of how it works. And at the end of my talk, I'm going to talk about my EU projects. I'm conducting, I'm the coordinator of two different European Union projects. And we are granted at a third one. And in fact, I'm looking for, students and a postdoc and etc. to work on those projects, okay? So these are fully funded projects by the European Union. Right? So at the end, I'm going to talk about what we are doing in those projects. So why do we need homomorphic encryption? This is the motivation part, all right? So, okay, so you are basically seeing all this, revolution happening nowadays, right? So we want to learn from data. So data is everywhere. We are collecting more and more data, and this data contains valuable information, right? So for financial or for economic reason, for the benefit of humankind, maybe those data is about medical, information or, genome, etc. Right? So we use like artificial intelligence, AI. We use machine learning. We use federated learning. I mean, probably you heard of those concepts, right? These applications and other algorithms to learn from the data. So this is perfect, right? Because as I said before, this data contains, valuable information for economical reason, for the benefit of humankind. But the thing here is that we can use these algorithms to learn or extract this information from this data. So, but in between us and the data, there is something called privacy, right? It stands between, its benefits and the data, because those data that I'm talking about, usually personal data, like your medical, records, your financial transactions, right? That you do. Okay, these are personal, and sensitive means that you have to protect them. And also, this data is not collected in one place. Probably this data is being distributed in different institutions, in different places, and fragmented. Right? Think about, medical data, right? So if you are doing, research in cancer, every hospital is basically, collecting its own information. But those information that is, residing in one medical institute or a hospital is kind of, not, very comprehensive maybe. If you just combine those data from other institutes or some other information about those, individuals, you can learn from it. And also, those data are protected by regulations, like there is what is called GDPR, General Data Protection Regulation. HIPAA is about medical data, or KVKK in Turkish, like Kişisel Verileri Koruma Kanunu. There are some regulations and rules and laws that basically protect the data. So this means that sometimes there could be some type of information that could never leave a certain hospital, certain database. But still, we wanna use this data. We wanna combine this data from some other type of data so that we can learn more about this data, okay? So homomorphic encryption is one of the most powerful tools that enables us to learn from data while we are protecting its privacy. How we can do it? Because in homomorphic encryption, you encrypt the data. You know what encryption is, right? And so what you can do, you can process and learn from the data while data is in encrypted form. You just learn from data without seeing what the data is about, without decrypting, okay? So you're just processing about, this data when it is encrypted form, which is nice, right? So like you just learn from it, but you don't really see the data. So this is, okay. All right, so I don't know how much you know about, cryptography, but, I just wanna basically give you the basics of the cryptography, right? There is something called public key cryptography, and whether you know it or not, you are using public key cryptography a lot. For example, more than 90% of the internet, transactions, like, is being protected by cryptography, especially by public key cryptography. And in public key cryptography is a simple case here. Maybe I can stay like here. So the mirrors message, we have a pair of keys in public key cryptography. One is public key, which is known by everyone. And you use public key for encrypting message, right? For example, here, E is a function, all right, that stands for encryption. It takes the message mu, and it takes the public key, and the result is the ciphertext. And I didn't show it here, but this encryption is probabilistic. It is using a random number as well to randomize the process. Even if you encrypt the data twice, the same data, same message, with the same key, it can produce a different ciphertext, okay? So this is the basic idea about public key cryptography. And public key cryptography, public key is open. Everybody knows about public key, okay? So it is not a secret thing. You can do the, encryption with the public key. In corresponding to this public key, there is also a secret key. And secret key is not known by everyone, is known by only the owner of the secret key. And what you can do with the secret key is that you just take the ciphertext, okay? If you don't know the secret key here, SK, ciphertext looks like a random, piece of information. You don't make any sense out of it, okay? So a result is going to be, if you know the secret key, that decryption function gives you back your message, okay? So that is the public key. You do the encryption with the public key, and you do the decryption by the secret key. And secret key is known only by the owner, so that the owner can do the decryption, okay? So this is the public key cryptography basics. Are you still with me? It's okay, right? So this is public key cryptography. Probably you know about this, but just to give you, the terminology and the background, so what we are going to talk about. All right, so I'm going to talk about fully homomorphic encryption. And fully homomorphic encryption is this. Okay, so I'm going to explain it over a public key because it's the most common usage of homomorphic encryption. Again, we have message, we have the public key, and if you encrypt the message with public key, this is what you get, ciphertext, okay? Ciphertext, if you do not the secret key, is not intelligible, right? So you don't basic, it doesn't contain any information about the message inside of the ciphertext, okay? And that, so we have two kind of homomorphism. One is additive homomorphism. For example, okay, so this is the ciphertext of the message mu, and the other one is the ciphertext of another message mu tilde, okay? So encrypted under the same public key here. So if you operate on them without decrypting them, and I just basically put some other type of addition operation here because, you know, this addition operation is defined over the structure of the ciphertext, whatever, you know, mathematical object it is in. So you have to basically apply this operation, whatever it is. Okay, so I'm going to basically give you the concrete, you know, construction of the the homomorphic encryption. So what happens here is that if you just basically operate on these, you know, ciphertext of two different messages, all right, and apply this operation here, so what do you get? So what is this? Anybody can tell me? This is the encryption of the addition of those two messages. Okay, so now you are able to add two messages without seeing what those two messages are. So this is a additive homomorphism. So this means that you can perform some addition operation, for example, over the ciphertext without seeing what the plain text are. You can do the addition. All right. What is missing here? Maybe you have to do the multiplicative homomorphism. All right. So in this case, again, you take the encryption of two different messages encrypted under the same public key. You apply some sort of a multiplication operation over the ciphertext without decrypting. You don't know the secret key. You don't see the messages inside of it. And the result is going to be an encryption of the multiplication of these two messages under the same public key. Okay. So what you did here is that you just multiply two messages. I'm assuming that these messages are being numbers. All right. Or you can, you know, basically represent any message by using some, you know, numbers here. So what you did here is that this is what is being, you know, full homomorphic encryption. Because if you have both addition and multiplication over the ciphertext, this is fully homomorphic encryption system. Of course, there is more to it, but I'm going to basically explain what that is, you know, what we need to know more about it, okay? So if you can perform both addition and multiplication, so this basically means that you can perform any operations over the ciphertext you want. So this means that you can basically perform any operation. You can compare the numbers, you can add them, right? You can sort them. See what I'm saying? So you can do all these operations over ciphertext without seeing them. Therefore, what you can do by using these two basic operations, you can process the data, you can train your, you know, AI models, machine learning models on the encrypted data without seeing the data itself. Okay, so this is a very powerful, you know, property of a particular encryption algorithms. Okay, does it make sense? Is it clear enough? All right. So I'm gonna, okay, you know, until 2009, we didn't have full homomorphic encryption system. The previous encryption algorithms either support addition or multiplication in homomorphism, not both. So these are partially homomorphic encryption schemes. And since 1980s, early 1980s, homomorphic encryption had to be what is called, had been holy grail of the cryptography. This is the most hot topic in cryptography. And in 2009, one researcher, one PhD student at Stanford University, you know, basically gave us the full homomorphic encryption scheme. Okay, so this is possible. So you have a question, right?
Yeah. So why do we use a public key instead of just generating a random key? Like,
but you wanna decrypt it at the end.
yeah,
You are going to use it because you have to have a public key and a secret key. At the end, at the very end, when you produce a result or computation result, you wanna decrypt it. And secret key is the one that you need to decrypt it. Of course, I mean, when you are generating public keys and secret keys, the key generation basic is random generation.
Like public key is not a single key, but it's a random key generated.
Well, it's
in
a
known
single key because you need the key, right? Because if you want to do the encryption and decryption, and if you want to do homomorphism, you have to use the same public key. Otherwise, it doesn't work. Okay?
Since we are decrypting even random state.
Random
State.
state.
Yes, randomized.
Yeah, there is a random number that you are using because it's a probabilistic algorithm.
But we have this both without both messages. How do we manage that? Because both are different.
Yeah, yes, that's true because you are going to a different random number here, a different random number here when you are doing this encryption at the beginning. And then this is going to basically, another ciphertext with another random number. But this random number, the new random number here is going to be a function of the random numbers of these two messages, okay? So, but what happens here is that during the decryption, this random factor is being basically factoring out, okay? So it doesn't important, it's not important. As long as you use any random here, the decryption process or the algorithm basically doesn't need to know the random number inside, okay? So that's the idea. Any other questions, or can I move on?
Do you use word homomorphic as the same in the abstract algebra? I mean,
Yeah, it is the same thing because as you see here, I mean, here, so there is here one, mathematical object, whatever it is. And so you do operation here, and then inside, this message lives in another mathematical object, and you do this operation here, and it applies in here. It is the same, meaning, yes.
then why do you not use some isomorphism but using homomorphism? Because this
Isomorphism is not the same thing, though.
yeah,
It's not the same thing.
it provides one-to-one matching.
Yeah,
But
homomorphism and isomorphism doesn't apply.
yeah, but when, for example, we apply homomorphism, there might be some same, for example, two elements might be mapped into the same element on the other domain. There might be some collision.
Not really. It doesn't happen that way. I mean, so you mean that this and this is going to be the same thing?
Might be.
Not very unlikely. This. It doesn't happen.
Husband of mine, they not know they could combine the both.
Yes, because there was no scheme. I mean, encryption scheme or a solution that basically combine both addition and because you perform multiplication, that's it. And in your computation you need addition, you cannot do it, then you have to stop. Or in other scheme, it only supports addition and it doesn't support the multiplication. But if you want to compute something useful, you need both, right? So multiplication and addition. So because it gives you a full structure, mathematical object. I mean, you can do an operation. Do I answer your question?
Yeah, you said you need different schemes.
The partial homomorphic encryption you're asking. And these, I mean, okay, I'm going to give you the detail right now. Okay, so this is what is called Payer scheme, Damgard-Burek scheme, and even RSA. Have you heard of RSA? Have you heard of elliptic cryptography? Even they are giving you some sort of homomorphism, but they support only one kind of homomorphism. Okay, so not or El-Gamal encryption scheme. They support one kind of homomorphism, but not both. This is why they were called partial homomorphic encryption. They support only either addition or multiplication. Okay. All right. So I'm going to talk about the actual construction. So it is lattice-based cryptography. Basically, we are using lattice problems, and maybe I should say more about the cryptographic algorithms. If you are using public key cryptography, the security of a public key cryptography depends on some the hardness of an underlying problem. For example, if you took the crypto course and you know RSA, what is the hard underlying problem in RSA? Factorization, right? So for example, if you are given a big number, very big number, like 2040, it is really big, and you know that it is the multiplication two prime numbers of equal size, 1024 with each. And but if you do not know the products, it is really difficult to factor them, because this is the difficult instance of integer factorization problem. That is the difficult. If you somehow find a very efficient algorithm for factoring very large integers, then you can break RSA. Since there is no such algorithm for very big numbers, so RSA is secure. Okay. And also, elliptic curve cryptography depends on what kind of hard problem. Anybody knows about it? Elliptic curve cryptography depends on what kind of hard or difficult problem.
Discrete logarithm for it.
Discrete logarithm, some sort of a discrete logarithm problem, because discrete logarithm problem is difficult when it is defined in a very large multiplicative or additive groups. So these are the mathematical concepts. But the problem, what is the problem with, integer factorization or discrete logarithm problem? What is the problem? So we don't really,
Like, it is very easy to do from one distance to other, but it is very.
but no, this is the property that we want, right? Because it's a one-way function, right? So you just compute, for example, discrete. What is the inverse of discrete logarithm? It is the modular exponentiation, right? It is fast and efficient to compute modular exponentiation, but the inverse of modular exponentiation is difficult, right? But no, this is not the reason that we are looking for different type of hard problems in homomorphic encryption, because integer factorization and discrete logarithm problems are easy to solve on some sort of a computers. What kind of computers? Quantum computers, right? Because what you can do, you can develop the very good quantum algorithms that can break RSA or elliptic curve cryptography easy. So therefore, what we want here is that we want a hard problem that is still secure in the presence of quantum computers. And that problems are coming from what is called lattices, right? I'm not going to go into the details, right? But I'm going to basically talk about one hard problem called learning with errors problem. And later on, I'm going to basically mention about the ring version of this learning with errors problem. What is a learning with errors problem? Anybody heard of it? What is it? Have you heard of this? Do you know the linear algebra problem, like linear equation system? All right. So in the linear equation system, you have certain number of equations, certain number of unknowns, right? And then there is a matrix on the left-hand side. There are unknowns again, there's a vector of unknowns. And on the right-hand side, there is some, numbers, right? So you can solve this linear equation system in which conditions?
You have at least n many equations, assuming that there are n many unknowns. If you have n plus 1, it is enough. If it is n minus 1, it is not enough, and you cannot for sure know which unknown corresponds to what value.
That's good. That's good. For example, if we have, if you know, or if you have n unknowns, and if you have n independent equations, linear equations, you can solve this. Can you solve this problem if the number of unknowns are more than the number of equations? No. Number of unknowns is more than the number of equations. Can you solve this? No, you can't solve it. But in this case, there will be more than one solution, right? Because if the number of unknowns are more, you can basically use them, and you can just choose them at random, and then you can basically solve the rest of it. Okay, as long as the number of the unknowns are equal or more than the equations, and these linear equation systems are, basically independent, so you can solve this equation system. But think of another case. So here is the thing, right? We have the matrix, vector of unknowns, and on the left-hand side, And on the right-hand side, we have some numbers, right? And then another vector, all right? So what if you perturb the numbers on the right-hand side? So this means that you have equations, but these equations are not exact. Okay? So it says, okay, a times x times plus n, etc. is equal to 5. Maybe not. Right? It's not exactly right. It's a little bit perturbed. For example, what you can do, you can just change the right-hand side, by adding some noise, error to the right-hand side of this linear equation system. And those errors can be sampled from a distribution. And this distribution could be a normal distribution with a very small standard deviation and with a zero mean, for example. So you just perturb, change the detail. So this is like learning with errors, right? You just change the right-hand side by adding some noise to the right-hand side. And that becomes a very hard problem. And that problem is difficult to solve even if you have quantum computers. Okay? Of course, I mean, people are trying to come up with some quantum algorithms to break it. A couple of weeks ago, and some mathematician came up with a new algorithm, and he was claiming that he could solve these kind of problems, but it turns out that there was a bug in his algorithm, and then now it is still secure. Okay, and the RLWE is a ring version of the LWE problem. Okay, I'm going to explain what they are. But first of all, I'm going to give you some mathematics. Is it okay to give you some mathematical background? Because I'm going to talk about math a lot right now, okay? So, of course, a computer engineer can talk about, okay? So, ring of polynomials. So, this is what it is. This phi of m of x is what is called a cyclotomic polynomial of degree n. And here we are using n is a power of 2. So, I'm going to talk about, and z stands for what? Integers, right? Set of integers. Z of x stands for what? Set of polynomials whose coefficients are integers, right? So I'm going to explain what they are. Okay, so what we can do here is that R, this ring, is this sort of polynomials of degree less than n with integer coefficients. So that's what it is. Okay, very simple. And when I say ring, if you took the crypto course, you remember, right? In a ring, we have how many operations? Usually addition and multiplication, right? So this is what we can do here. But here, the elements are not regular numbers, but polynomials of degree n or degree less than n. So how do we do addition? Well, you have two polynomial whose degree is less than n, at most n minus 1. You just add them component-wise, right? Coefficient-wise. That's what you do when you do addition in polynomials. How do you do multiplication? Okay, the standard polynomial multiplication, but when you multiply two polynomial of degree at most n minus 1, and the result is a polynomial of larger degree, 2n minus 2, which is not the element of this because I'm talking about polynomials of degree less than n. So therefore, what I'm going to do is that I'm going to, divide this polynomial, the large degree polynomial, with this xn plus 1 and get the remainder. But this polynomial, to do division with this polynomial is very easy because whenever you see xn or something, some coefficient in the polynomial whose degree is n or more, you can use the equation xn is equal to minus 1. Xn is equal to minus 1. If xn minus 1 is xn is a minus 1, then what is xn plus 1? It is minus x. So the division here is very easy operation. You just take the upper half and subtract from the lower half. That is the reduction. It's very easy. And this is the reason why I'm picking, polynomials like that. Okay, so this is the operations. Okay, we have a ring of polynomial ring of polynomials whose degree is less than n with integer coefficient. This is how we do addition. This is how we do multiplication. Remember in the previous slide when so my ciphertexts are going to be not messages, but they are going to be polynomials. Okay, so therefore I'm going to perform, when I say addition, it's going to be this polynomial addition. If I say multiplication over ciphertext, I'm going to talk about this multiplication. All right. So when I put Q here, so it is the same ring, but this time the coefficient of these polynomials are going to be modulo Q reduced. It cannot be Q or more than Q, right? So we have to basically perform reduction operations over there. Okay, so that is the basic what we need. Okay, so we just say this is the ring that we are talking about. So the coefficients can be from 0 to Q minus 1, and the degree can be at most n minus 1. So these are the type of polynomials that we are going to work on. Are you still with me? Is it too much math? But you are here, for this math, right? Okay. So here, for example, if I just say A is a polynomial like this, I'm talking about, this polynomial whose degree can be at most n minus 1. And AIs, as I said before, they are reduced modulo Q. And normally we represent numbers from, modulo Q from 0 to Q minus 1. But here we are using a different approach, and we are using AI like this. Let me give you an example. If Q is 7, normally we use 0, 1, 2, 3, 4, 5, 6. We are not going to use that representation. We are going to use this. It's like more balanced. So it's like distribute evenly around 0. You're going to see why we want to have this kind of, representation rather than from 0 to Q minus 1. This is unbalanced. This is balanced representation. It should be, evenly distributed around 0. Okay. So that is the example for this. Of course, in cryptography, this n is quite large, at least 2,000, 4,000, 8,000, right? It's very, very large numbers. All right. So I'm going to talk about the error distribution. So here, when I say this means that A is sampled from this distribution, meaning that the result is a polynomial in that ring. And the coefficients are sampled from a normal distribution with 0 mean and standard deviation sigma. All right. When, this standard deviation is small number like 3.5, 3.2, etc. So, and then this polynomial is going to be something like this, right? It is going to have coefficients, very, very small numbers distributed around 0, right? And you have, basically -1 and 1 more likely. And if you go from the 0, those numbers are going to be less likely than the smaller numbers. So we call this kind of polynomials small polynomials because their coefficients are small integers that are distributed, around 0. 1, -1, 2, -2, it goes on like this. But if some of the numbers are going to be less likely. All right. So for example, can we have a bound or practical bound for the numbers that you sample from this normal distribution if, the mean is 0 and the standard deviation is sigma? Okay. So can you basically give a practical bound, meaning that whenever you sample, from this distribution, the sampled integer is going to be small. But what is the probability of it being very large? Okay, you can arrange that. All right. So this means that, for example, if you have a normal distribution with 0 mean and standard deviation sigma, this error function gives you the probability that a sample lies in -a and a. And the complement of this function is error function complement. And this is the probability that sample lies outside of minus A and A. So if you basically pick B0 large, relatively large, like for example, 10 times sigma, and the probability that your samples lies out of or larger than B0 is very unlikely, very small probability, like 10 to the power of minus 20. It will never happen in practice. So therefore, if you pick B0 sufficiently large, not very large, of course. For example, if you, for example, your sigma is 3.5, you pick B0 35. So it is sufficiently large, upper bound for the samples that you sample, for the integer you sample from this normal distribution. Does it make sense? So this means that B0 is kind of a practical probabilistic upper bound on the sampled integers. Does it make sense? Or, okay. So then I'm going to talk about the hard problems, okay? In the ring LW problem, we have two types of hard problems. One is what is called search problem. What do I do here is that I pick A and S, from this, I can just say in an arbitrary way. And E is the error polynomial sampled from this error distribution. Let's assume that these are being uniformly randomly selected here. And E is noise or error polynomial. All of them are polynomial, by the way, right? But it is a small polynomial, meaning that its coefficients are small and sampled from this normal distribution. Then I compute this. A times S plus E. Modulo Q means that these are polynomials, remember, and I reduce their coefficients modulo Q. And result is B. So the hard problem is this. I'm not going to tell you what S and E are. I'm going to give you A. I'm going to give you B. And I'm going to ask you, what is S? And this is, again, very, basically hard problem. It can be as hard as some of the hardest lattice problems. So here you can just see this is like a linear equation system defined over polynomials. The only difference is that we have this noise polynomial. If you do not have this, you can solve this. Okay? But if you basically perturb the right-hand side of the equation, okay, then the problem becomes very hard. We are going to use this one. And the other one is a decision problem. It is basically very common in cryptography. So that should be, very difficult. Okay, it's very related, but this problem should be also difficult. Okay, so what I do here is that I just play a game with you, right? In one case, I may be choosing B uniformly at random, like a random polynomial, or I can generate it pseudo-randomly by, doing this calculation, A times S plus E modulo Q. And I'm going to give you A and B, and I'm not going to tell you which method that I use. And you tell me that whether I generate B like this or like this. You cannot basically, tell me. All right, maybe I can, generate two instances of A and B, AB and A prime, B prime. And I use, for example, this method for one instance and the other method for the other instance. You cannot tell which one is which. Okay, so that is what is called the decision problem. And these are hard problems, as hard as the hardest lattice problems, and they are not vulnerable to, or they are resistant against the quantum computers. Okay, so this is what we want to use in our construction. Okay, so I'm going to basically use, use these properties, use this mathematical background to basically construct my, public key crypto system. And a typical public key crypto system, consists of three functions: key generation, encryption, and decryption. In homomorphic encryptions, we have to define some other functions as well, homomorphic addition and homomorphic multiplication. All right, let's start. What am I going to do? I'm going to pick two integers. Okay, let's call them, prime numbers. And here, Q is much larger than P. And here, P is the plain text modulus. So this means that my plain text cannot be larger than P, right? And Q is my ciphertext modulus because, plain text and ciphertext live in different mathematical construction, right? We work modulo P in the plain text and modulo Q in the ciphertext. And Q must be much larger than P. And so to make it simple, P is equal to 2. Okay? Just meaning that I'm just adding or encrypting 0 and 1. Are you still with me? Is it too much math? No? Is it okay? All right. Okay, and this security depends on the ring dimension of n, q, and delta sigma, and usually again very large, thousands, 2,000, 4,000, 16,000, 64K, etc. All right, these are the, I'm not going to talk about how they are being selected. And these are public domain parameters, meaning that everybody is using the same public parameters. And here, as you see here, I'm going to sample those polynomials from this distribution, meaning that S and E, they are small polynomials with small coefficients. And A is selected as a polynomial whose coefficients uniformly random from 0 to q, but minus q over 2 and q over 2. And so this is how it is being, computed B. And here, A and B, they are the public key. You just give it away. And secret key is S. This is what you keep it to yourself. Knowing A and B, can you compute S? I just told you this is difficult, right? I just told you to explain that, the only difference here is that I'm just multiplying P, E with P. That doesn't matter. It doesn't change the hardness or difficulty of the problem. Okay, so this is the public key and this is the secret key. And so here, I'm going to do encryption here. Mu is RP, meaning that this is a polynomial. You have to encode your messages as a polynomial. I'm not going to go into detail how you do it. Is an arbitrary message that I'm going to, encrypt it. The way I encrypt is like this. I'm just, again, sampling noise from this normal distribution. These are small polynomials. And then compute this. As you see here, mu is the message, right? And I compute this. And my ciphertext has two components, two polynomials, C0 and C1. Okay? So in C0, we have mu. In C1, we don't have mu, but we have the public key. We are part of the public key. So this is my encryption. How do I do the encryption? Very simple. You do this calculation. You just take the second part of the ciphertext, multiply it with S, and subtract the result from C0. And then, of course, you are going to do this everything in modulo Q. The coefficients are going to be reduced modulo Q. And you work with polynomials here. At the end, you are going to do modulo P. Reduction, because remember your message is in modulo P, so you have to reduce, because at the end of this you can get something larger than P, but you have to reduce. When you reduce it, that guarantees you or gives you the message itself. How? Well, it's very simple. So you can just think that the decryption vector is like that, and secret is like this, and the correctness of decryption operation, you just put C0 here, C1 here, and multiply it with S. You arrange those things. So as you see here, so these are the multiplication, the small polynomial, multiplication of small polynomials, right? And multiplication of two small polynomials, and they are being computed, multiplied by P. So this means that whatever we have here is a polynomial result, and its coefficients are going to be a multiple of P. At the end of the operation, we have to we just basically apply modulo p. What happens if we apply modulo p at the end? So this small means that it's a polynomial with small coefficients. What happens here? If you reduce, okay, so you get something here, but you know that this is mu plus some polynomial whose coefficients are the multiple of p. What happens if you reduce it modulo p?
We eliminate them.
You get rid of this. And what you get? The message itself. But there's one condition. What is it? You will get mu, but you have to be careful there.
Must be relatively.
Hmm?
Mu must be relatively.
No. Okay, so modulo q. Okay, so pay attention modulo q. Here. Anybody would like to make a comment on this? Yes, you will get mu, the message, original message at the end, but there is only one condition.
I will take my chances.
Yes.
If mu is modified because of modulo q, then it will be some altered version, and then when you apply modulo p, then it will be again changed.
You are
So-
close. Very close.
Most probably you're assuming that mu is not modified because of modulo q, as it stays in the original form, and when you apply modulo p for the whole thing, then it is the original message.
Mhm.
Otherwise, it will be, as I said, some altered version of message.
So when mu is being modified? If
Bigger than.
That's very nice. Very good. If you know this number becomes larger than q, then it is going to be reduced modulo q. Then the number is not gonna give you, I mean, it's gonna be somehow modified, right? It's going to be perturbed. So this means that you are, and also make sure that we are not working modulo q over 2, right? Because we want them between minus q over 2 and q over 2. Okay? So here, you have to be careful. This number shouldn't be larger than q over 2 or smaller than minus q over 2. Its absolute value should be strictly smaller than q over 2. If you can guarantee that, and that is going to give you, all right, so the message back, this operation. And so are you familiar with this notation, this infinity norm? Okay, so these are all polynomials, right? So infinity norm means that the largest coefficient. Okay, so that is very simple. If, for example, what is the largest value of mu? Which is p, right? Because message cannot be larger than p. So if this is smaller than q over 2, reduction doesn't happen. Modulo q reduction doesn't happen. And you preserve the message here, and the decryption is successful. Okay? So it is indeed you're going to keep. Okay, so then correctness constraint must be this. I'm not going to go into detail, but if you okay, so here all these polynomials as E0, E1, E2 they are small polynomials, meaning that their coefficients are not very large. This is why we are, basically picking them or generating them as small polynomials. And but what about if you multiply two such polynomials? Yes, the result is going to be a polynomial slightly larger, coefficients, but they are still small. So this means that you can basically make a guess and find the upper bound. For example, remember this B0, this is the upper bound for the coefficients of those polynomials we just mentioned. So we know that none of them can be larger than B0. Of course, can be larger, but with very negligible probability. So this way we can just say, okay, all these polynomials, coefficients, or infinity norms, smaller than B0. Okay? But what about, I'm going to talk about this. This is what happens when you multiply on a small example. Okay, so for example, if m is 8 and n is 4, and by the way, this cyclotomic polynomial is going to be like the x to the power of 4 plus 1. So this is when you multiply two polynomials like this, degree 3, you are going to get this. And from this, you can get that none of the coefficients can be larger than n b0 square, right? So this means that those coefficients are going to be smaller than, strictly smaller than this. A bit low upper bound, you can find a stricter upper bound, tighter upper bound, but that's okay for explaining all these things to you. All right, then we can have an upper bound E1, which is B0, but for A times E0, E times E0, this is the upper bound. For this, we have this upper bound. And at most, so therefore, this guy, we call it the small one eta, right? P times eta time plus mu. And if we plug the upper bound for all this, so we are going to have this, okay? So what is this meaning is this, if you basically, if you know the sigma, you know what B0 is. All right, we can calculate B0 given sigma, standard deviation of the normal distribution. If you pick the P as your plain text modulus, then you compute Q. I mean Q, how big Q must be. So you have to pick a Q for ciphertext modulus, satisfying this inequality. Okay? So if you pick P and Q in such a way, then you can do decryption easily without any problem. Okay, so this is the general idea. You don't have to follow every mathematical detail here, but the idea here is that I'm gonna use a little bit, maybe 5 or 10 minutes. Okay, it's okay? Good. So I'm gonna basically do this correctness constraint. So now I'm gonna basically explain to you this is a fully homomorphic encryption, meaning that it supports additive homomorphism and multiplicative homomorphism, basically. Okay? So this is the definition just for you to remember the additive homomorphism and multiplicative homomorphism. So let's start with additive homomorphism. And consider two ciphertexts, C and C tilde, that encrypts two different messages, mu and mu tilde. So this means that we have those. Remember, the ciphertext has two components, C0 and C1. So what am I going to do? If I basically apply the decryption operation using the secret key, so this is what I get. P times eta, which is a small polynomial, right? You know the conditions. And for the other ciphertext, we have this. What happens if I add those ciphertexts, C plus C tilde, meaning that you just add C0 to C0 tilde, C1 to C tilde, and then, multiply the result with the secret key, and you are going to have something like this. But at the end, what you get is this, right? Mu plus mu tilde, modulo P, of course. But here, you have a similar thing, but this time P times not one small polynomial, but a small polynomial from the first ciphertext and another small polynomial from the other ciphertext. You add the small polynomial. So this means that the resulting ciphertext is going to have more noise. Okay? So this means that, well, you can still do that. As long as this is smaller than Q over 2, modulo Q reduction doesn't happen, then you can still decrypt this, resulting ciphertext, and at the end you will get mu plus mu tilde modulo P. Okay, so you do the homomorphic addition here because you just add ciphertext C and C tilde of two different messages, and if you decrypt the result, you are going to get mu and mu tilde, but you have to be careful, right? So this should be smaller than Q over 2. So this times Q must be a little bit larger, right? In normal, if you want to do homomorphic addition. All right, so upper bound, you can compute the upper bound. This time, it is not P times B, but 2 times PB. So how the noise increases? Does it increase linearly or quadratically? If I perform one addition, the noise doubles. If I add 3 ciphertexts, the noise is going to be 3 times more. So it is basically increasing linearly. Noise increases linearly. All right. What happens if you add more, ciphertext like that? So it's going to be, depending on the number of ciphertexts you perform addition, your noise factor, your bound is going to be L times P times B. So this means it is indeed, the noise increases linearly with the number of homomorphic addition you perform. So therefore, you have to pick Q and P in a proper way so that decryption is possible. But no matter what you do, the error term is going to exceed Q over 2, right? Of course, you can, select a larger, larger Q, but eventually, so decryption becomes impossible, because if you perform more addition than you can, then this is going to be larger than that. All right, so then decryption is not going to be possible because this reduction, modulo Q reduction, is going to happen. So this is why this means that we can perform only limited number of additions of ciphertext. When you set, fixed P and Q values, that gives you the budget, right? You can perform this many number of additions. You cannot go on like this forever. So this is why it is being called not fully homomorphic encryption, but somewhat homomorphic encryption. All right. So this means that you have a budget of additions or homomorphic operation. You can perform that number of additions and the homomorphic addition, but you have to stop. Otherwise, the message becomes undecryptable. All right, so multiplicative homomorphism, I'm gonna basically, go fast here. The only thing that you have to understand is that we do much more with complicated operations. Here, if you do multiplication, noise doesn't increase linearly, but quadratically. So this means that it, grows very fast. Okay. So this means that in that sense, multiplication is more expensive operation. Okay, you have to basically select much larger Q if you wanna basically support one multiplication. If you wanna support 2 multiplications, Q should be larger. If you support more multiplication, complicated circuit, your Q is going to be 1,000, for example. It's going to be very large. And then you are going to need a larger degree polynomials and etc. So this is the idea about fully homomorphic encryption. Of course, there is a way of, how do you say, okay, you go on like that, and then at certain set, okay, your budget for homomorphic encryption, you just use it up, right? You have to stop. But there is another way, it's called, another function called bootstrapping. So it's a little bit costly operation, but if you apply, I'm not going to explain bootstrapping, I'm going to stop in a moment. If you apply bootstrapping is going to basically, you apply it, very expensive operation, because you are working in a very large, the degree polynomials and etc. So you can basically eliminate most of the noise. And then you can start over. And by applying bootstrapping, function, you can go on forever. And this is the one fully homomorphic. Fully homomorphic encryption means that you can perform any operation and you can, perform as many homomorphic operations as you want. So this is indeed fully homomorphic encryption. This is possible only using bootstrapping. All right, but I'm not going to explain it to you. All right, and finally, I'm going to talk about my 2 EU-funded projects. One is Encrypton, and we are the coordinator, and we are basically working with 3 different European universities. So, in fact, you understand this. I just talk about big, a large degree polynomials and large integers and etc. The drawback of homomorphic encryption is really nice operation, by the way, nice, construction, but the only drawback is that it's very slow. You have to accelerate. And we are using a different like GPUs, FPGAs, and like vector instruction, etc., to speed the things up. Okay, so this is the Encrypton project, and so this is a privacy enhancing technology leveraging homomorphic encryption. So we are looking for, undergraduate, master, and PhD students and postdocs to work in this project. We have funding for that. And last year, I have received another project with Kameroja, probably know Kameroja. And another one is the Face for AI medical privacy compliant health data as a service for AI development. Here, as I said before in the very beginning, so the European, they just want to, basically create what is called a European health data space, meaning that we just want to put, the data, medical images for certain diseases like prostate cancer, lung cancer, Alzheimer, ischemic stroke, medical images about those diseases, all right, in one, big data space. And then we just want to work, run some AI algorithms on those data spaces. The problem here is that those data are about human beings, individuals. And usually all this data are being protected by some regulations, and hospitals cannot give away those data or share this data for these purposes. Therefore, you have to protect them, okay? For example, here, our job here is to basically come up with some federated learning algorithms. And then every hospital or medical institute, they are going to basically develop their own local model, right? For example, the perceptron, XGBoost algorithm. But the local models are only as good as the local data. But if you combine data from different institutes, from different medical institutes, you have more and richer data. And then if you train your models on data from different institutes, your model is going to be better and more accurate, right? But those medical institutes and hospitals cannot share this data. What can they do? Everybody develop their local models, and these local models are being encrypted, all right? And we just get the local models in encrypted form, and we just basically, for example, do something on the local models, like averaging some of the coefficients and etc., homomorphically without seeing them, of course. And then the result is going to be a more accurate global model, and we are going to share it. But we are going to do it without seeing what the actual local models are. We're not going to see the data. We're not going to see the local models, because local models may contain some information about the data itself. All right. So these are two projects that I'm basically coordinator. I'm managing, and there will be another one starting on October or December, October, November, or December, which is called Pre-DIB-MEVA. All right. So this is also again related to homomorphic encryption. Homomorphic encryption, I just talked to you about the one application of homomorphic encryption, but homomorphic encryption is basically, you can just think that this is like a building block for many other advanced cryptographic algorithms, such as the one that we use zero knowledge proofs and blockchain algorithms, because in the end you are for example verifying a transaction in a blockchain, but the idea here is that you are not supposed to see the content of the transaction. Can you do it? Yes, you can do it using what is called the zero knowledge proofs. Have you ever heard of the ZK-SNARK, ZK-STAR type of thing, zero cache algorithms, the blockchain? Yeah, I mean, these are quite popular, especially in financial institutes, and there are many startup companies. And I'm sorry for the overtime, and I can take questions now. Okay, I'm done.
Thank you for the great lectures. Do I understand correctly that there is some limit for addition and application.
Yes.
After that, we cannot decrypt the message.
That's true.
And the question is, why we need these operations and how many operations we need in real life for
That
application?
depends on application. For example, in the case of, let me give you a concrete example that we are working on. For example, in the federated application, learning applications, you don't really need very deep circuits to many operations. I mean, averaging is just enough, right? Just addition, basically. Okay, so you just do addition, and you don't. Most of the time, you don't really even need multiplication. So this means that in federated learning, certain federated learning applications, you don't need many operations like that. But if you want to run the full, for example, so the CNN network, for example, and then you perform addition, multiplication, and many addition and multiplication one after another, then if this is the case, then you have to select larger parameters. Okay, because remember, P, this is the P is for your messages, right? And Q is a ciphertext. And if you want to have more operations on the ciphertext, and you have to select Q. And depending on your application, you have to select very large Qs, or relatively smaller Qs, and the other parameters as well. And that depends on your application. In certain cases, they are not very big, but in certain applications, that depends on your application, what you want to do with the data. Do I answer your question correctly? Satisfactorily. Any other, Ece?
So we are using the distribution to use some noise randomized parameters. But in real life, we can do this randomized operation. We are saying that it is quantum.
But it's not. Wait, I'm sorry. Finish your sentence.
Okay. What's the difference with these two randomized operations? Not vulnerable by other side.
Again, this is not about randomization, because RSA use random numbers when it's encrypting. Elliptic curve is using random numbers. They are all modern day public key crypto systems, whether you are performing encryption or signature scheme, they use random numbers. All right. So this means that random numbers are serving for different purposes, which is called semantic security. I mentioned this, in crypto course if you took it, and this is for, how do you say, semantic security. But the strength against the quantum computers lies in the fact of that you use the different hard problems. Remember the RSA. RSA, you can break RSA if you can factor large integers. In conventional computers, you cannot factor large integers. But there is what is called the Shor's algorithm, which was invented in 1994 by Peter Shor, is a mathematician. And he showed that, well, you can if you have a large enough quantum computer, right, you can factor the integers easily. Even if you select much larger integers, still vulnerable. Because integer factorization is not a hard problem for quantum computers. Discrete logarithm problem is not a hard problem for quantum computers, but they are hard problems for conventional computers. But when it comes to the hard problems that I mentioned here, so maybe I can go this problem. Okay, so this one, right? Even quantum computers do not know how to break them. Because somehow these problems, meaning that you select ANS from this ring, and E is a small polynomial sampled from this random distribution. So this becomes, meaning that I give you DNA, and I just basically ask you to find S. This is a very difficult problem. Even if you have quantum computers, we don't have an algorithm for computing S easily. You don't. And it is still not, for example, these are still very hard problems in quantum. But do I answer your question? And maybe you are asking about, so this random number, right?
Yes, something from.
But this random number is for, you know, making this problem harder. But for the other one, when I used for decryption, these are different random numbers. These are for randomization also. Okay? So these are randomization. These are two different things.
I asked it because you said that if we don't have the noise in the part, we have A and S.
Yes, that's true. You know, in this case, yes, because if you do not have E, it becomes like a linear equation system. You can solve it. But I don't give you the linear equation system. I just basically, perturb or add some noise to the equation system. And this noise doesn't have to be a large noise. If you sample it from a normal distribution with a small, standard deviation, it gives you a secure algorithm, secure system against both conventional algorithm in computers and quantum computers. I don't know if I answer your question.
Yes.
Any other question?
So mathematics here, is it more of applied or is it more of pure math?
It is not pure math, absolutely, by definition, because we are using them here. So this is applied, very applied. But of course, here we are using number theory. We are using abstract algebra. We are using linear algebra. And we are using, all sorts of different mathematics here. And these are not pure. But of course, when people are working in lattice, for example, and it was, I don't know if there is any other application of lattice. Lattice is in I don't know. But here in cryptography, we have very good applications. These are mostly applied.
One more question. If I was working a cryptography job, will I be dealing more with like computer things or more with mathematics?
That's up to you. That's up to you because, if you want to work in the mathematical constructions, if you are a mathematically oriented, person, and you can work in the mathematical part. And if you are more like computer engineer or you want to develop some, codes for it, then you can work in the computer side. And our group, we are in the applied side. We are implementing those things in efficiently. But of course, we need and interact with mathematicians as well, because some of the constructions here, I just basically, this is very simplistic, very overly simplified version of what we are dealing with here, very simplified. And the real thing is that it's much harder to understand. So at the end, we are computer engineers, computer scientists, and our mathematical knowledge is limited, even though we can follow many things. And sometimes to understand some of the constructions, mathematical foundations, we work with mathematicians. So this means that, in this kind of research, both mathematicians and computer scientists, electrical engineers, statisticians, whatever, and they basically work. But of course, they work in different, aspects of the problem. Mathematical part, for example, you can, work on this, and you can just work on, for example, try to find a quantum algorithm that can break this system. And there are many mathematicians, very theoretical mathematicians, who are trying to do that. As I, mentioned in the beginning of my talk, and like a couple of weeks ago, and Utku basically was smiling at me, Hocam, your, algorithms are broken. Somebody wrote a paper, and then he claims that, some of those problems that I claim to be, hard and difficult on quantum computers, and this guy, this mathematician, claimed that it is not that, difficult. But I think 1 or 2 weeks later, and 2 other mathematicians studied his paper, and in one of the algorithms they found a bug, and then the mathematician admitted he made a mistake, and he admitted that he didn't find how to fix that bug. Okay, so this means that this is secure, but this is always the how cryptography works, right? Because when I say integer factorization problem is difficult to solve on conventional computers, do I have a proof for that? Can I say nobody can invent a better integer factorization algorithm? Can I claim that? Can I provide a mathematical proof? There is always a possibility in cryptography that someone can come up with a better algorithm to break, unbreakable system. But also cryptography, this sort of cryptography is full of people who break the RSA, for example, many times. And because like maybe 15 years ago, I attended a conference, and the invited speaker was Ronald Rivest. And Ronald Rivest, if you know RSA, Ronald Rivest is the R in RSA, right? He's a computer scientist and kind of a mathematician at MIT. And he told us, joking though, because in a jovial manner, he was saying that, every week I receive messages from all around the world who claim to break RSA. But it turns out to be not true, right? Yeah, but again, cryptography is like that. So this means that we work on assumptions. Assumptions are that certain problems are hard on conventional computers, not hard on quantum computers, or some hard assumptions that some algorithms, some problems are hard on both in conventional and quantum computers. So that is the case of cryptography. Am I clear on this? Any other questions?
Hocam, recently I heard about the paper you mentioned, and I heard about some criticism about the lattice-based cryptography because people claim that the lattice-based approaches are very young relative to, for example, prime factorization maybe being discussed since the 30s. I don't know.
Yeah,
it's
maybe
a very
2,000-year-old problem.
But
yes,
lattice structures maybe 100 years old problem,
That's true.
or maybe younger.
That's true.
So some people
They
say
have a point. Yes.
we are still in danger, some people say, and maybe they can find some quantum algorithm or even maybe a classical, I don't know. My point is, what could be an alternative? For example, yes, we have lattice-based approaches, and what are the
Coding-based cryptography. Coding-based cryptography, for example, if you heard of Michaelis crypto system or Michaelis codes, and they were invented in 1970s, or not, they invented before, but they proposed for cryptographic usage in 1970s, and coding-based cryptography. They are also secure against quantum computers. But some people claim that there is a, relationship between the coding theory and lattices. So because, when I explain some of the lattice problems, real lattice problems to a coding theorist, and he says, okay, it sounds like a coding theory problem. And also the good thing about, there are some algorithms based on symmetric key cryptography, hash functions. Have you heard of hash functions? And there are some hash functions. What was the name of this hash function, Utku? No. The one that is being Sphinx. Yeah, Sphinx, for example, is a hash-based algorithm, cryptographic hash, and most probably it is secure against quantum computers, because usually against quantum computers, so the symmetric key crypto system like AES or hash functions are more secure than public key crypto system, because in public key crypto system we have abstract algebra, number theory, we have more structures, and more structures we want in one hand, but those more structures also may mean vulnerability to exploit, right? But in symmetric key cryptography, you have less structures, so this means that symmetric key cryptography, like cryptographic hash functions, and if you build some cryptographic algorithm, they are more likely to be secure against quantum computers. So these are the alternatives. If lattice-based cryptography becomes vulnerable, I don't think so in the near future, then we have alternatives all the time. Any other questions?
is lattice-based encryption in today's world commonly used for being less vulnerable to quantum computers, or do we, for today, mostly use it for privacy concerns and such?
Well, homomorphic encryption, if you are using lattice-based cryptography for building a homomorphic encryption system, this is for privacy concern. But there is also another effort, which is a standardization effort, because right now, the IBM is building trying to build a quantum computer, and Google, they are trying to build China is putting billions of dollars to build the quantum computers. There are many startup companies trying to build quantum computers, and there is a Canadian company called D-Wave. They are selling quantum computers, and people are so there is a insecurity, right? We are basically relying on RSA, elliptic curve cryptography. If they are broken, so this means that internet is broken, right? As I said before, 95% of our web traffic is encrypted by RSA, elliptic curve cryptography, or RSA. If they're broken, so therefore there is a new standardization effort, and there are a couple of algorithms that were selected for standardization, and there are 3 of them, right? Kyber, Dilithium, and Falcon. 3 of them are based on lattice-based cryptography. So now many companies are investing in lattice-based cryptography. They are building chips to perform simple encryption and signature. Why? Because they believe to be secure against quantum computing. Because quantum computers are coming, they are building a larger and larger quantum computers. So therefore, if you want to have secure internet communication, we have to switch from elliptic curves to quantum safe, quantum secure algorithms. And lattice is the most, prominent one. All right, maybe we should stop here.
Thank you very
All
much.
right, thank you very much. I took too much of your time, and thank you.
Thank you for coming. Hope to see you again, maybe next week, Mondays. We will have another Math Plus seminar. So again, thank you all.